अरे ये बोलने से मैं इसमें भेज
Good afternoon, sir.
Good afternoon.
Sir, actually some participants are just joining, so just we are waiting for 5 minutes. After that we will start.
Okay, no problem.
Thank you, sir. Yeah, Namaskar. Good evening to one and all. Welcome again. I, Vipin Chandrapal, coordinator of this event. Welcome to all on the fourth day of 1 week online faculty development program on recent research trends in control, instrumentation, and allied engineering, a multidisciplinary approach, RRTCIA 2020. Today we have with Dr. Yogesh Singh from NIT Silchar. Good evening, Doctor
Good evening.
Yogesh
Good
Singh.
evening, sir. Good evening, sir.
So, Dr. Yogesh Singh graduated in Mechanical Engineering from Government College of Engineering, Jagdalpur, Chhattisgarh. In 2008, he received MTech degree in Machine Design from National Institute of Technology, Rourkela, Odisha. In 2012, he got his PhD in Robotics from IIT Indore. In 2016, he then worked as postdoctoral fellow at Indian Institute of Technology, Bombay, from January 2017 to July 2017. From August 2017 to July 2018, he worked as an assistant professor in the Department of Mechanical Engineering at SRM Institute of Science and Technology, Chennai. In July 2018, he joined the faculty of the Mechanical Engineering at National Institute of Technology, Silchar. His main research interest includes kinematic and dynamic modeling of robotic manipulator, parallel manipulator, and nonlinear control of robotic system. He has published more than 30 articles in top-class journals and conference proceedings. Now, good evening, sir. So now I request Dr. Yogesh Singh, please start the session. Please, sir.
Thank you very much for the nice introduction. And now I'm glad to present here about my research work and some handful session. So you can also do some practice on this particular handful session, that is the kinematics of robotic system. So before going to the handful session, it will take around 10 to 15 minutes. So before that, I will show how to, first of all, some mathematical system development is required to do the simulation of the kinematics of any robotic system. So uh, with my research exposure, whatever I have done during these years, so I will explain that one in little bit, and also I will let you know what are the things uh, uh, is required for the simulation purpose. Okay, so I will start with the some like a part. Suppose there is a lots of robotic systems are available. Even you can distribute it in majorly two types. Okay, so first of all, that is the serial robotic system. It's like your one hand, your human hands from the uh, your fingers to your elbow, uh, and your there will be a different joints. Okay, so that can be mimicked as a one kind of robotic manipulator. So in technically we call this type of robotic manipulator is a serial manipulator, and other one is a parallel manipulator. So I will let you know what are the difference between these two. So now why the topic itself, you can see the kinematics of robotic motion stage. So in which I will let you know what is the motion stage first of all. So like already you have seen in some lathe, some CNC machine, some lathe machine in your workshop, or somewhere in your daily life. Okay, so those particular motion is you can say the stages which will work in the x motion, x coordinate motion, y coordinate motion, and z coordinate motion. So that is called as the motion stage. Okay, now that particular motion stage can be developed also by using some other phenomena. Okay, which we call as the parallel robotic system. Okay, So why we need this kind of thing? So that is our uh, introduction part. So why we need the need of semiconductor industries, like to making a very minute part or miniature part. Okay, we need to have some kind of motion stage that can develop it, that can make that particular model, which is in the range of micron or nano. Okay, or it will be used in the MEMS microelectronic mechanical system. So that also we can use. Okay, issues in the current available instruments for the motion stage, for that, like a CNC machine, you can just assume imagination, you just visualize that CNC machine. So we can hardly work up to the millimeter range, but not in the case of the micron range. And also it is a very bulky structure. Okay, so without using 5 to 10 people, you cannot move it. Okay, if you are manually, you are going to move it, or you need some extra machine or extra robotic system to move from one place to another place. As a third one is the maintenance problem. Okay, once it will be shut down, you have to looking for the maintenance, and it takes a lot of days to shut down, and your time or money will get uh, resolved on those process. Okay, so another one is so lots of mechanisms, lots of systems are available, that motion platform available, which are we are using. Okay, so those are from the very good companies like Newport, Rockwell. I think you have heard about the psychic instrument and Aerotech. Okay, so they, whatever the machines you have seen, that those all are in the basis of serial kinematics or serial machine. Okay, so one actuator means the motion requirement. Okay, so one actuator is going to connect with the second actuator by serially. Okay, and each actuator should be active. Okay, then only your operation can be performed. Okay, but I am telling about the you can see here in this image only. Okay, in this image you can see there is a serial manipulator. Okay, so I think some of you are already familiar with this kind of robots. You have seen in some college, some industries. Okay, but this kind of robot we didn't saw. Okay, this kind of robot is hardly available. Okay, so you can see in this particular systems we call as a serial manipulator. So one end is open. Okay, and every here see you see some motors are installed to move the system. Okay, so these motors are very in a serial manner. Okay, and each motor have to be function as a active joint. Active joint means each motor have to run, each motor have to be powered. Okay, to perform a single task of the end effector. So this is called as end effector. Okay, but in the case of this robot, you can see here two motors are only installed. Okay, and there is a no other motors, only joints are there. Okay, like a pin joint. Okay, and these are the end effector which is performing some operation. Okay, so you can see only two joints are required, or two motors are required to function this robot. Okay, and that it is situated in such a place that it should not harm or affect the movement of this robotic system. Okay, so it will. So you can see the difference between these two. This is bulky. This is very compact. The joints are very means every joint should be proper function, but here only the base joint are function, other joints are passive. Okay, and here you see the open space is higher, but here the open space is lower, but this can be worked out in a very precise manner. And this if you suppose you are getting error in your joint, so it will accumulate, means this joint has some error, so this joint again have some error, then this joint again have some error, so it is adding. Okay, and you will get a higher error. But here the base error only is implied, other errors you can remove it. Okay, so this is the one good way or important point for this particular parallel manipulator. Okay, so now that parallel manipulator also have a category like a planar case or a spatial case. So planar case means which will be useful for the working only on a plane. So you can say this particular robot is working only on the plane, means this is the XY plane. So it is just coordinating or making some trajectory or following some path or doing some operation only in this particular plane. But you can see the spatial condition here. So it can not only fix with this single plane, it can move also or rotate also. Okay, so more than one plane it will work. So that is called the spatial, and this is called as a linear, sorry, planar. So this is some very simple difference and definitions of the serial and parallel robot. I'm not going for the more technical view. So this is the very simple definitions. So now, so we need this kind of robotic systems. Okay. So for the doing some development or some operation or making some a small component, miniature component. Suppose here you are installing some depositing material kind of instrument, okay, in the end effector. So it will try to make some kind of a very small part, okay, so that can be used like it will act like as a 3D printer, you can say, okay, but it is very like in the miniature component, like very minute in the micron or nano level also it can go, but the latest available platforms are not that much comfortable for the micron level or nano level. Okay, so these are the some platforms are available which is work on the nearby the micron level. Okay, so these are the some platforms we have. This is for the planar case and this is for the spatial case. So you can see again here something you have, some welding machine you have. Okay, so now you can you can move your component as per the user requirement. Means you need some object is there, you need some 4 holes on the object in 4 different we can say the locations. Okay, so how you will do, you have to fix some welding machine here, so the movement can be done by this particular platform. Okay, the same thing can be done here also. Okay, so so this is not fixed. This is only fixed with the micron level. It is not less than the micron level. Means it will not go for the nano level. Okay. So for the nano level, there is some development is going on. So I will let you know some development regarding that. So suppose these are the some development like XY positioning stage or COM drive. Okay. So here you can see we are using some different kind of actuators here. Okay, so this is some you can say uh, some kind of piezoelectric actuator, comb actuator we are using to get the uh, uh, very minute level of precision movement. Okay, so how much movement is there? This much. So this is the 55.4 micrometer square. Okay, so that much position or movement we can get using the different kind of actuators. Okay, so here what is happening in the last cases, these are the motors. Okay, so with the use of the motors, getting the level of micron or level of we can say the nano level, we cannot move. Okay, because this is itself is a very bulky. Okay, so this is the platform, you can say. This is connected with this actuator. So these are the not only your motor that is connected with the slider or the ball screw. So it will the rotation is directly converted into the translation. So these 3 translation are again connected with the some passive joint. Okay, and now the passive joint is connected with this end effector. So because of these connections and only these 3 movements, this end effector can move in X direction, Y direction, and rotate about Z direction. Okay, so this is the one phenomena here. Okay, the same thing is happening, only we are going to change these actuators. Okay, so these actuators can be a piezoelectric actuator also. So in that piezoelectric actuator case, we are getting this much workspace. same as some other actuators we can use, like a voice coil motor, voice coil linear motor. Okay, and with the use of voice coil motor, again we can get like a 170.5 micrometer range of movement. Okay, so here these four actuators are nothing but your piezo, sorry, that voice coil motor. Okay, so these are the some other actuator we are using now. One more concept is there. We can use. We can also go with the smart materials. Okay, we can also use some other kind of actuator. So it can. It may further improve the movement of our manipulators or platform. Okay, so what will be those kind of thing? Okay, so before that, I will show you the research I am doing on that particular way. Okay, so I am doing a research on the this particular manipulator. Okay, so these are the some manipulators I have. Okay, so what is happening here? You can see. I will present you one simple manipulator. So this is one simple manipulator. Okay, so there is a like a thousands of possibility of making these kind of manipulators based on their joints, means actuator. Suppose here you can see these blocks are there, two blocks are there, two blocks are there. There is some triangular plate is there, some lines are there. So I will explain everything. Okay. So here you see uh, the some representation like this is our reference frame. Okay. So X, Y, and this is zero origin frame, and this is connected with three actuators. You just visualize there is a three actuator, that is the translation actuator. Okay, it can move, it can translate this direction, this X direction. So this is the first translation, this is the second translation, and this is the third translation. So that is related to R1, means first translation is R1, second translation is the R2 of the block, and third translation of the block is R3. Okay, so now this three translation can be act as a actuator. Okay, so this can be any kind of actuator. Your motor screw, motor lead screw combination, piezoelectric, smart material. Okay, so the basic concept is how it will looks like. This is a translation one direction, second translation, and third direction. Okay, now there will be another three blocks. You can see this is one block, this is second block, and this is third block. Okay, so what is this? Now on top of the first translation, okay, second translation, second block is taken away. Okay, here. Okay, and again here the second block is there. So these two blocks are very fixed. Okay, now in this block there is a one hole. Okay, one circular hole you have. Okay, so in this circular hole, one simple rod kind of thing, you just imagine there is a one rod kind of thing is there. So these three rods are kept. Okay, now this one end of these three rod are connected with a plate, that is a triangular. Okay, now what is happening? One translation is there, second translation will happen due to this rod. Okay, once it will move like this, you just imagine if it will move like this, what happened? Because of this joints, rotation joint, because of this translation joints, okay, it will try to move, this platform will try to orient or move in some x, y, or theta direction. Okay, so what happened? Once you will move this one, it will move. Okay, and this is fixed with that one, so also it will move, so it will directly follow a x direction. Okay, so this is, suppose this is your x direction, so x movement you will get. Suppose you are going to move this translation joint and this translation joint. Okay, so both in the same direction, in this direction. So what happened? It will try to, this is two are also connected with this one, and this is fixed and this is fixed, so it will try to move in the this direction. So that will be your y. So you are getting x translation, y translation of the end effector. Okay, now suppose you are going to move this object. Okay, because this is only the power joint, others are passive, these are the power joint. Okay, so you are moving this one downwards and you are moving this block upwards. So what happened? It will try to rotate this this plate is trying to rotate because of the revolute joint. Okay, so you are getting a rotation theta about z direction. Okay, so this is the three movement you will get of the motion. So that can be converted as a, what we can say, that can be converted as your motion platform, or that can be used for some stage platform that can be hold your object for some operation. Okay, so this is the way we are doing some research on this one. So for that we need to first identify for further experiment, for further development of it. This is the concept. Now for the further development, we have to use some mathematics behind this. What will be the mathematical model? Then once the mathematics will be over, then only we can say the what will be the workspace, or how much workspace it can cover. Okay, so that those all kind of things can be done with the use of only mathematical modeling. You have mathematics, then only you can do it. Okay, so for that, for any robotic system, we need to go with the two kind of mathematics. One is the forward kinematics, and second is the inverse kinematics. Okay, so forward kinematic means what? Means you want to know what is x, y. That is the final goal you are waiting for to get it. Okay, so what will be the x and y in terms of your rotary, your joint value. So what is the joint value here? R1, R2, and R3. Okay, so you want to get how much your x, y in terms of, in function of R1, R2, and R3. Others are known to you. Okay, you don't know only x and y. You know the geometry of the plate. You know the R1, R2, R3. So you can directly get x, y, theta. Okay, so this is the way we are going to get it. First one. Okay. Second one is called as the inverse kinematics. Okay, so what is the inverse kinematics? Inverse kinematics means you want to get what is the value of R1, R2, and R3 in terms of, in the function of x, y, and theta. Means you know the path. Means you have some, you just imagine that you have some object. Okay, you want to you want to go for some hole on the object you have. Okay, for that you know how many holes you need, like 4 holes you have. So you know the holes locations on the object. Okay, means you know the xy location of each hole. Okay, so once you know the xy location of each hole, then you will put it in the end effector. Okay, so your major task is now to find out what will be your, means how much your joint will translate, then only you can get this x, y, and theta. Okay, so this is the one type of analysis you have to do. Then only you can just validate your simulation, that how much workspace, how much it can go. Means you have given some location, and suppose that location will not allow to move your R1 that much. Okay, so it is not possible for your object to move. Okay, so for that you need to first analyze that whether these particular locations are possible or not. Okay, so this is the one way we have to do it. So that is for the inverse kinematics. Okay, so inverse kinematics are very important part for the planar parallel manipulator, but forward kinematics are very important for the serial robotic manipulators. In the inverse kinematics, that is not very complex. You can see this is a very simple relationship. So now this is the R1, this is the R2, this is the R3. R1 in terms of x, y, theta, R2 is also, and R3 is also. Okay, so it is not that much complex. But once you will derive the forward kinematics, you can see there will be very much trouble you will get to solve the forward kinematics of any parallel manipulators systems. Okay, so that is the specific one. So that method, suppose I got it, some inverse kinematics, forward kinematics, and I want to find out the how you have some circular trajectory. Also you have given that your systems move like a circular. This platform can move a circular way, like some circular trajectory you have given. So you have given some circular trajectory, and you want to move your object. So how it will move? That animation we can do it. Okay, we can perform that analysis. Okay, so that I will show you by the program itself, in the Matlab. Okay, but before that, we will see some research progress in this particular field. Okay. So we have taken that manipulator and we performed some like a SolidWorks or some modeling, okay, and made it in software. Now after validating the software, what we have done, we have gone through some we can say in the real time validation. Like in the real time, we made the same prototype, okay, and then perform some experiments, some trajectory, whether it is moving same or not. Okay, that is for the millimeter range, not for the micron range. Then we have made some CNC milling machine. Okay, so that is for the micron range. Okay, we made it for it. Okay, so this is the way we are doing using these particular systems. Okay, so this is the milling machine accuracy. We run lots of time. This is the trajectory we have given. Okay, for the end effector. So move starting point is this, and it is moving like first it is following this horizontal line, second vertical line, then circular, and then ramp, and then again ending here. Okay, so this is the path it is following. You can see there is a different type of color. So it is a different type of run. After every setup of run, we have taken the values and we have checked that the trajectory is followed or not. So you can see the error is very less. Okay, the error is itself in the micron level. Okay, so you can see here the error itself in the mean is in the micron level. This is the millimeter, so you can say 5 micron. Okay. So after using that milling machine, we have cut down. We have taken some sample like aluminum plate. Okay, in this aluminum plate, we have taken some different trajectory. Like we have given like a square one. Okay, of the milling spindle. Okay, so it will cut in the square one. So you can see that is correctly doing like circular shape also, triangle shape also, and one complex shape, as I in the previous slide I have discussed. Okay, then the same thing again we have replaced with the whatever we have done with the, now we are replacing with the shape mereolite. This is the shape mereolite sheet. Okay, so this is the shape mereolite sheet. Now this is the primary stage and this is the secondary stage. So what is the quality of shape mereolite? Shape mereolite quality is that means once you will deflect it, okay, it will change its we can say shape. Okay, now once you will hit it, it will directly get its original shape. Okay, so that is the one phenomena here. So we have used this one for the translation actuator. Like we have deflated first it using some wise coil motor, and then we have heated back that one. It is regaining its shape. Okay, it will act as a translation to and fro motion. Okay, so this translation motion we used for further development in the motion platform, and we have done some research on that, and we find that it is correctly followed the system. So you can see here, this is the platform itself. Now here we are using the shape mereolite spring. Okay, instead of using some slide like a motor ball screw, we are using shape mereolite spring. Once you will this is first one is elongated, second one is compressed. Here also one is elongated, one is compressed. Now you have given some trajectory to your system. Okay, so how it will follow? With the use of this actuation model of this spring only, it will follow. Means once you will heat back this elongated one, so it will try to compress, another one is elongate. Okay, so we will make some type of arrangement to fit it to find the some trajectory values. Okay, so this is the one phenomena we are right now doing. Right now we are working on our laboratory. Okay, so this is some experimental model we have done. You can see these are the simple springs are there. These are the links. So we are giving power to that. It will try to move in this direction. It will try to move in this direction. It will try to move in this combination of this three translation motion. We can move our index factor. Okay, so these are the different experiments we have done. We have moved the first prismatic joint, second, third, and what will happen once we will move the first and second. first and third, second and third, first, second and third simultaneously will move. So what will happen? So these are the some different values are there, and we find this particular workspace. Okay, so you can see this red one is workspace. Okay, so this is the good behavior we are getting. We are getting the almost a square kind of workspace, means your manipulators can move within this particular range. So how much range it is? This much, 65 to around 130. Okay, so 65 to 120 means how much it will be? It will be around 60 or 65. Okay, so that much coverage we can do in the both direction. Okay, so 65 centimeter we can move, and up to the range of 1 micron. Okay, so this is the thing which is happening. Okay, so this is also, so our manipulator's workspace is like that. It can go higher range also, as well as the lower range also. Okay, so what will be the lower range? Less than 1 micron, and what will be the higher range? Okay, greater than 35 centimeter. Okay, so this is the one part we have done. Now I will show you the, as I explained, that one handful session on robotic kinematics using Matlab. So here you can see this is the one model we are going to make. Okay, so how it will work, how we will make it. Okay, how we will animate it. So you can also try in your home. Okay, or for any robotic system, not for only this. You can for any robotic system. Only the needful is that you should know the relationship to find out the forward kinematics and inverse kinematics. So forward kinematics is nothing but finding the xy in terms of the joint value, and finding the inverse kinematics is finding the joint value in terms of end effector value. Okay, so this is the way. So what we have done here, okay, the same thing we have taken. Okay, so simple, this manipulator we have taken. Now they have given some circle trajectory to the end effector, means the x, y and theta value I have given already. Suppose you know that your object should move like a circle. Okay, your object should perform a trajectory like a circular trajectory, you know it. Okay, so you have given some circular trajectory that lasts up to the 10 plus 3, means up to the 13 millimeter. Okay, so it will go up to that one. Okay, maximum 13 millimeter. Okay, so it can be a radius of like a 6.5 or 7. Okay, approximately. So that will be there. So now what happened? We have given some trajectory value first. Then we have to decide the given value. What will be the given? You know, now you know x, y, and theta. So you want to get what will be the R1, R2, R3. So for that, what values you want to have other, again, means with you other geometry, like plate geometry you have, how much the length of A, what is the height of this triangle, what is the side length of the triangle. Okay, so this is the value you have, the side length, the horizontal length, the width of this from this origin position to this one, what is the largest range you have. Okay, so it is given like a 20 centimeter. Okay, now after that, what will happen? Okay, after that you have to decide, you have to write your inverse kinematics and forward kinematics in terms of formula only. Okay, so suppose you are getting some for as you can see, this is R1, R2 and R3 only. So R1 you are getting x plus h sine theta, y plus a by 2 sine theta, y minus a by 2 sine theta. So y, this is I, we are giving some steps, like it should run from 0 to 10 seconds. Within 10 seconds you have to complete your circle. This is the time step we have given. Okay, so for that we have given like what is your S1, S2, R1, R2 and R3. So this is the value we are getting. Okay, so now once you have given this one, then after we have to define the forward kinematics formulation. So this is nothing but x is equal to S1 minus, means some relation we have. Okay, some mathematical relationship we have. So we are writing these two formula. That is very important. And this other formula is related to only what will be the, you can see here one length is there. This is L1, L2 and L3. So what will be the length L1, L2 and L3? So this is the one relationship we have. Okay, so these three relationship we have given. Now once you fill this all relationship, means you have given S1 L1, S1 L1 you have given geometry for S2 and L2, you have given for S3 and L3. Okay, so you have given the end effector, means the end point of finishing of this S1 L1, S2 L2, S3 L3. So that's why it is written here. What will be the S1 L1 S1, what will be the L1, what will be the S2 S3. So you have given some X coordinate and Y coordinate for that particular value. So suppose here what will be your S1 L1, okay, what will be your S2 L2, what will be your S3 L3. So it will directly deduct, once you are given geometry, then it will directly deduct, and these 3 points are there, which is making your triangular plate. Okay, which is making your triangular plate, which is exactly same as whatever you have given. A is equal to 4, H is equal to this much. Okay, once you have given this this plot, okay, once you have given the fill axis or filling of those points, okay, then after you have to decide others length also, actuator also. So how it will looks like this one. Okay, suppose here you have, once you have decided this circular plate, now circular point you have already given. Okay, so now once you fill this block, so you have to give the coordinate of this one: x1 y1, x2 y2, x3 y3, x4 y4, x5 y5. Okay, so this is nothing but the same only: x1 y1, x2 y3, x3 y3, x4 y4, x5 y5. Okay, so this 4 box you have given. So that box is nothing but you are going to make this relationship, like this is your first S1, this is your S3, and this is your S2. So now once all these three are, you are going to fill, you are going to use the fill command, then it will try to directly fill this length L1, L2, L3 as well as S1, S2, S3. So you will get this particular relationship. Now you can see in the Matlab code directly. This is for the left. So you can see so you can see here. Is it visible to you, my Matlab code? Okay. Okay. So now you can see here, we have given some 10-second value project. Then after we have given some trajectory. So that's the same trajectory we have given. Then I have defined like what will be the inverse kinematics or what will be the forward kinematics. Simply you write your equation. Okay, that's it. Then after you have to give, your length. Someone's speaker is on, please off it. Okay. So now once you will make this relationship, then after what you have to do, you have to use a fill command and make a triangular plate. Okay. So that is nothing but a relationship of S1 L1, S2 L2, S3 L3. Okay. Then after, once you will use it, then after what you have to do, you have to use a plot command to make the blocks N L1, L2, L3, S1, S2, and S3. You are making this one. You are highlighting this one. Okay. Once you make these three, this relationship, you will get this is over. Okay. Once you will make this is over. For any robotic system, you have to only consider only this inverse kinematics, forward kinematics. Other one is your how many joints you have. Okay. Like this here, we have in the interface 3 joints. So that's why we have taken the, you start S1, L2, L3, then again start S1. Okay. So that triangular platform is there. So you are starting like a S1 something, L1, L2, and then again S1. Okay. So like that we have to make our relationship for X coordinate, for Y coordinate. Okay. Because in the plane we are working, so it is X and Y only. Okay. So this is the way we are doing. Now once you will going to run, see how it is going to be function. It will function like a, once you run it, you will get this particular value for this particular system. Okay. Now once I will run it again, so it will show how it is. So animation is not possible here. Okay, so animation is not possible here. Okay. This is the way we are getting. Okay. Okay, then this is the way we are doing our work. We can model it. We can make some simulation out of it. A simple kinematic. There is nothing dynamic. For dynamics, it is very large. Okay, you have to first define the some method to find the equation of motion, then you have to do it. Okay. So for the kinematic analysis, you can do a simple analysis like using some forward and inverse kinematics. You can make this relationship, and you can check whether your system is working or not. You have given some trajectory, some path, that path is followed by the system or not. Okay. Once you are satisfied with the result, then you can model it. You can go for the prototyping for that particular system. Okay. So this is the way we are doing for the research work. Okay. So now if you have any question, you can ask. Okay. Dr. Vipin?
Sir, it's Dr. Sudipto Chakraborty. Sir, please tell.
Yeah, so you ask some if any means the participant have any questions, so they can ask.
Okay. So participants, if you have any question, then you may ask. Also, you may write in the chat box. Sir, let me check in the YouTube section whether they have asked any question or not.
Okay.
Sir, till now there is no questions.
Okay.
Participants, you are requested to put your questions and doubts, whatever you have, in the chat box. Sir, I think there is no questions from participant side.
Okay. Okay then. So I will finish my session here only because I just reserve for 15 minutes for any question and answer. This is only one simple handful session. Okay, so if I will go continue for some other one, it will take time.
Okay, sir.
Yeah.
Okay, sir. Thank you so much for being with us. And we have really enjoyed your session. And that was wonderful. We hope that in future also you will be with us and your presence will grace us in this way. Thank you, sir.
Thank you. Thank you very much.
So participants, with that, we are concluding this session here. So next session will be starting right after some time. You can have a break for 5 minutes. So please be with us. And next session we will start shortly. Thank you. All participants are requested to fill the feedback form of session 14. You can find it in your chat box, also in YouTube. So please fill it as soon as possible and wait for the next session to be continued. Thank you.
Hello, Namaskar. Good evening to one and all present here. I hope you all are safe and sound at your end. I, Dr. Anukumar Sharma, coordinator of this event, welcomes you all on the behalf of organizing committee on the fourth day of 1 week online faculty development program on research, fluence and control, instrumentation and allied engineering. Today we have on guests Dr. Ramvyas and Parsuraman as an eminent speaker. Very good evening, sir. We have an honor to have you as an eminent speaker for the day, sir. Dr. Ram Vyas N. Parsuraman is an assistant professor in the Department of Computer Science at the University of Georgia, Athens, USA. His research mainly focuses multi-robot systems, network autonomous vehicles, intelligent robot teleoperation, and human-robot interfaces. Previously, he has had postdoctoral researcher positions at Purdue University and KTH Royal Institute of Technology, Sweden. He conducted his doctoral research at the European Organization for Nuclear Research, CERN, and obtained his PhD from Universidad Politécnica de Madrid. He was a recipient of the prestigious Marie Skłodowska-Curie ESR Fellowship and is an alumni of the IIT Delhi. So, I welcome, now I would like to request Dr. Ramvyas and Parsuraman to share his knowledge and words of wisdom with the participants of this FDP. Dr. Ramvyas, you may please share your presentation and you are now open to participants.
Thank you very much, Anup. Can you all hear me?
Yes, sir.
Great. So there's no problem with there's no intermittent connection, right?
Yes, sir. You are audible, sir. No problem.
Okay, great. Thank you very much. Thank you for giving me the opportunity to present this topic in this faculty development program. I'm going to share my screen. Can you all see my screen? Are you able to see my screen? I don't hear you, so I don't know whether. Anup, Dr. Sharma, can you speak with your unmute? Yes, okay, good. Okay, good. So I'm going to start the presentation then. Thank you all for waiting in the evening time for my presentation talk. So what I'm going to do is I'm going to cover some of my recent works related to multi-robot systems. And specifically, I'm going to talk about how can we exploit network connectivity, graph theoretic tools to enable or achieve multi-robot control mechanisms. So as Dr. Anup Sharma introduced me, I'm Ramvyas Parsuraman. I'm directing the Heterogeneous Robotics Research Lab at the Department of Computer Science in the University of Georgia here in US. So before moving to the actual talk, I just want to give you a brief bio sketch of mine, and then I will introduce the general mobile robot, field robotics domain, the motivations for why my research, why I'm doing my research in this multi-robot systems and field robotics in general. And then I will also give you some introduction to the basics that are necessary to understand the research part, such as the graph theory and multi-robot control. And then I will move on to the core research that I want to talk about today, which is the graph-aided or using graph theoretic tools to achieve multi-robot control. And specifically, I will talk about three different research. So the first one would be about how do we achieve multi-robot consensus control using wireless networks. That means given a wireless network connectivity graph of a mobile robot system, multi-robot system, then how can we achieve rendezvous? Consensus means all the robots agreeing on a specific point to meet, or a meeting at a specific point, which is otherwise called rendezvous. So I will I'll talk about how can we achieve the consensus control if we have a wireless network graph. And then I will talk about how can we again achieve multi-robot rendezvous using distributed mechanisms. How can the robots talk to each other in a distributed manner without a centralized controller in place? And then how can we use hierarchical graph tracking mechanisms to achieve the same rendezvous objectives, but from a different application perspective. And then I will move on to introduce the third part of the research that I'm going to talk today, which is how do we split the robots into multiple groups, and then how do we make these groups heard through a group leader. So a group leader, a robot leader, will first gather all their group members, which is rendezvous in the first place. And once they achieve the rendezvous, or once the group leader can reasonably bring all the member robots within a specific radius, then it should be able to herd them, take them together to a common destination, which only let's say the group leader can understand where it is. So again, we are going to use graph theoretic approach to achieve these multi-group herding as well. Yeah, so this is general outline for my talk today. So my research interest, I am generally working in resilient and robust control and communication mechanism for multi-robot systems. In addition to that, I'm also working in effective human-robot interfaces and also human multi-robot interfaces, and then also associated machine learning mechanisms that are methods that are required for achieving adding intelligence to the robots and also adding perception abilities to the robots. So I have worked in the past in multi-robot consensus and formation control mechanisms, and general mobile robot motion planning, especially when there is a intermittent communication or when the communication is challenging. And also I have worked with wireless connectivity awareness through teleoperation interfaces, so that for the teleoperators of the mobile robots understand how the wireless connectivity is around the mobile robots. And I also work in multi-robot systems. For instance, how do we enable multi-hop communication capabilities in multi-robot system through relay robot control mechanisms. So as Dr. Anup Sharma said, I am currently an assistant professor at the University of Georgia. Previously I have worked at Purdue University and KTH in Sweden. And before that I have worked at CERN, and I did my PhD in the University of Madrid in Spain. Okay, so let's move on to the problem domain, which we are going to talk about today. Just the field robotics and then multi-robot systems from the perspective of field robotics. So many of you might be familiar with what mobile robots are, what are their applications, what are the scope, what are the current state of the art, and so on. So, however, I just want to give you a basic introduction of how a mobile robot could be useful. For instance, a mobile robot could have multiple different forms, right? So it can be drones, which can fly and much more dexterous compared to ground robots. In the bottom left, you can see a ground-tracked robot we call UGV, unmanned ground vehicles. So equipped with this particular robot, equipped with the robot manipulator. And also they have multiple sensors suite on board the robots to do many autonomous capabilities. So you can also see, you might also seen humanoid robots. There are many applications for humanoid robot as well. For instance, in space, for instance, in the International Space Station, they have recently used using a humanoid robot to do some assist with the autonomous repair. And humanoid robots are also finding new applications in domestic scenarios as well, in elderly care, as an assistive technology as well. And there are also well-defined or well-known applications of ground robots, especially when it comes to search and rescue, disaster kind of scenarios where the robots can help humans. I'm going to talk about that motivation soon. So there are multiple different types of mobile robots, depending on the mobility capabilities, depending on the sensing capabilities, depending on the computing capabilities and actuation capabilities. So I want you to understand the domain of field robotics in general. So that means the mobile robots operating in unstructured and dynamic field environments. So this is completely different from domestic or industrial scenario where everything is structured and known beforehand, so that we can design those the applications of those robots carefully. But in a field robot scenario, the intention is that the robot should be available to be deployed with a short amount of time. So without knowing about these environment beforehand, and also the structure, the environment could be dynamically changing, so that when you deploy a robot today, it may not be the same scenario tomorrow. For instance, let's assume a post-disaster condition where the situation is evolving every day. So the robot should be able to adapt to such dynamics in the environments and unstructured scenarios. So one of the strong motivations for the field robotics is how can we reduce hazards to humans by applying robots instead. So for instance, in scientific or nuclear facilities, how can we reduce human exposure to radiation, nuclear radiation, for instance, ionizing radiation, or in cases of search and rescue, urban search and rescue, and how can the robots work alongside with human to assist them and make them more efficient and effective in saving victims, saving lives. And those are time-critical situations where each and every minute is important to the first responders. So how can we enable robotic applications in such difficult scenarios? And also, field robotics have different other applications. For instance, agriculture robotics domain is completely different. The structure can be predictable. It's not dynamic, but still there can be multiple different challenges associated with this deploying robots in agriculture environment. And also, robotics have strong applications in military, defense, infrastructure, like such site survey, for instance, and then mines to do some survey in the mines, and then also aerial robotics applications, which you might have some understanding of. Okay, so coming to the motivations again about reducing the human exposure to hazards. So one of the work I did was at CERN, where you might be familiar about CERN, especially when it comes to Large Hadron Collider. There's the Large Hadron Collider is 27 kilometers circular tunnel underground, 100 meters underground, and so the Large Hadron Collider is a big mission which needs to continuously be operated. But then there's also a cycle in which they follow. So they operate the machine for 3 weeks, and then they shut it down for 1 week for maintenance and repair. And during this 1 week shutdown period, they will send human radiation inspection personnel first to ensure to measure the radiations in several different zones, and then make decisions accordingly to whether to limit how many number of persons to allow and how long should they be allowed, because both time and the distance are crucial for the risk of hazards. And in this case, it's ionizing radiation is the hazard here. So instead of humans doing this site survey or doing some maintenance operations, the idea is to replace the human role with robots to do at least the inspection and survey operations, in addition, if possible, manipulation and also maintenance. Because the robots can tolerate much higher hazard levels, radiation levels in this case, and also help can coexist with humans in this scenario, and then can help humans to make their task more efficiently and effectively. So another strong motivations for these field robotics research is, again, in a natural or even artificial disaster conditions, then it's chaos everywhere. Then how can first responders can effectively use robots as tools for them to help, for instance, search victims, search damaged properties, analyze the situation, and analyze and understand the situation, and then make the decisions accordingly, or even, for instance, survey the damage made by those disasters. For instance, the robots have initially been deployed after the World Trade Center collapse in 2001, but there have been they have shown what are the challenges associated with the robots. For instance, the communication, wireless communication is a predominant challenge when it comes to deploying robots in a real-world scenario, because the communication those days were highly intermittent, highly unpredictable and unreliable, but especially because the robots have to transmit a large amount of data and also receive a large amount of data back for them to control it effectively. And recently, in one of the European projects that I was working in, we deployed robots after this earthquake in Matlab, Italy. So we deployed multiple ground robots along with aerial robots working together to assess a damage made on a church, which is a very historical 400 years old church in Amatrice. And the robots were able to effectively produce a 3-dimensional map of that church. And also we realized a lot of challenges associated with real-world deployments as well. So these kind of real-world deployments of robots in those difficult situations will help us understand what are the limits that we must push the state-of-the-art to, and also how much the robots can be useful in such real-world scenarios. And also on the right side, you can see robots deployed in a post-Fukushima nuclear accident in 2011. They have used several robots, but also they have lost several robots in those while they use, because of challenges, again, when it comes to the communication and also debris everywhere that makes the robot difficult to navigate. And one of the robots, for instance, got stuck in in the second floor, and humans cannot retrieve the robots, because the idea to have the robots in the first place is to not have hazard exposure to the humans. So if we lose these robots in such important critical applications, that destroys the whole motivation to deploy the robots in the first place. So we should design the robot control mechanism such that it should be tolerant to failure and tolerant to noise of data. Now, I want to talk about multi-robot systems. So far, introduce you to general field robotics, single robot kind of scenario, how multi-robots can be useful. So if you look, if you think of how single robots can be useful in those kind of situations, multiple robots can in fact increase performance and dexterity of that the robots can do, and type of tasks the robots can do. and it adds scalability, flexibility, redundancy, and so many other advantages compared to single robot system. And arguably, multi-robot system is difficult to control compared to single robot system because it adds more complexity on the other hand. So we should think of the multi-robot control problem also from the perspective of how can they achieve any control in a distributed manner so that they can talk themselves without needing a centralized controller in place, because they cannot always have a centralized system to in an unstructured and dynamic scenarios. And also, multi-robot case system can work alongside with humans in ensuring that their task can be done more efficiently and effectively. Okay, so enough of the introduction. Now I would like to move on to the background that I want you to aware of before moving on to the research. So the first one is about multi-robot control. So what are the control challenges for the multi-robot or control needs for the multi-robot system, and also what are the basics of graph theory that helps us to enable some control mechanisms for the multi-robot system. So here our agents are again mobile robots in a field, real world field environment, and the assumption is that, or a very important challenge, is that we cannot have global map of the environment beforehand and also on an online basis, because the robots have to coordinate between themselves to create the global map, which is already an inherent challenge in itself. So the assumption generally is that all the robots have their local maps based on whatever the sensing capabilities it have, and also they should be able to share some of the data so that they have some global perspective or some global information, but not full complete map. And also, robots are distributed in the environment, and they can only perceive or communicate with the neighbors. And this also makes the real-world application more realizable. And also, there can be heterogeneity in the within the multi-robot system. For instance, some of the robots can be UGVs, some of the robots can be aerial vehicles, and some of the robots in some situations, for instance, if you're thinking of an oil spill analysis or search and rescue in a marine scenario, there can also be unmanned surface or unmanned underwater vehicles that can be useful. And when you have a multi-robot system, then there are multiple networks or multiple levels of network of local interactions that can arise. Mainly depending on the locality of the robots, so the sensing range of the robots and the type of sensors being used on the robots. For instance, laser scanners have a wider range, but much limited. Some laser scanners have limited angle of view, and there are also some cameras, omnidirectional cameras, or even omnidirectional laser scanners that have wider angle of view, but also limited range. And some sensors, like active sensors, they are one-dimensional, or even sometimes zero-dimensional, so they can only measure points. Some sensors, like infrared sensors, can measure the distance along the lines, so they are sometimes two-dimensional or one-dimensional. And the current state of the art used in the industry, for instance, in self-driving cars, they use the three-dimensional LiDAR, like Velodyne LiDAR, that are on top of the cars. That has interesting properties both in terms of range as well as the accuracy or the resolution. So depending on the sensing and the locality of the robot, the communication, the multi-robot has a limited, so the robot can sense their neighbors and communicate with the neighbors. And they can also adjust their range to, for instance, if some robot doesn't have enough energy to operate, then they have to adjust the range so that they can save some energy or even bandwidth. So given these are all online characteristics of a robot, and So depending on them, they have to communicate and coordinate with their other robots in the network. And as I said, there can be huge differences in the sensing capabilities, especially when it comes to whether a robot can sense in all directions, omnidirectional, or it can only sense in specific direction. So directional sensing. Like here, you are seeing two different examples. If it's using an omnidirectional camera, you can see the neighbors in all directions compared to a Kinect camera, which can see only in specific front view. And also, for multi-robot control, we can design several interaction protocols that these fundamental interaction protocols, I would like to say, so to achieve more advanced control mechanisms. The fundamental protocols are agreement or consensus, we call, which can also be sometimes referred to as rendezvous problem. And then there are also other fundamental protocols like formation control, coverage control, swarm control, and then distributed estimation, state estimation. So these are fundamental protocols that are necessary to have on a multi-robot system, for a multi-robot system to achieve more advanced control mechanisms for these robots. And specifically for this talk, I'm going to focus much on the agreement and consensus problem. So multi-robot control has several applications. I've just gave one of the example. For instance, let's say the application here is to increase the communication range and network throughput of a human first responder or firefighter in a real world. So what he has with him is, let's say, there are multiple robots that can autonomously move. Their only objective is to make the human communicate effectively with the ground station. So then how can these relay robots, we call, which stands in between these humans and the ground station, that can convey the information from the ground station to the human, final human operator. And then how can we increase throughput in such a, for instance, such an application? How can we enable autonomy of these relay robots in such an application? So these can be interesting challenges. So for instance, here you can see the robots are trying to track one robot, follow a robot, trying to track the leader robot, which is leading, let's say it is following a specific human firefighter or specific human end user. And these robots are using their sensors. In this case, it's wireless communication device, directional antenna sensors to track the other robots, the direction and the distance, so that it can form an effective range and throughput for this end-to-end network. Okay, so coming to the basics of graph theory. So you can view a network of robots as graph. So where each robot is a node in the graph, and then the link between the robots are edges in a graph. And depending on the sensor range, the sensing capability, whether omnidirectional or directional sensing, we can have two different type of graph, either undirected graph or directed graph. So undirected graph means, again, if they have omnidirectional sensing capabilities, or if and also the information is bidirectional. And on the other hand, in a directed graph scenario, the robots can probably either sense or communicate in only one direction, and also they might have constrained field of view or sensing field of view. So generally in graph theory, a graph is represented as a set of nodes, V, a set of edges, along here, and then set of weights that comes that can be added or can be attributed to the edges. And graph theory has shown a strong potential in robotic networks, and it's a great tool for analyzing networks in general. It has potentials. It has applications in social networks. It has applications in wireless sensor networks, and so on. And so there can be two type of graph, directed and undirected graphs, as I said before, where in an undirected graph, it just represents the pair of nodes in which they can communicate, and this is bidirectional in general. Whereas in directed graph, you have edges that represents the node from node to the tail node to the head node, so they can only be one directional communication. They can also be bidirectional in some cases in directed graph, if you have the edges that happens on both the ways. And the neighborhood of a vertex or a node is generally defined as a set of nodes with which this particular robot can sense or communicate with, or that has edges too. And in graph theory, you can define an adjacency matrix, where which is a symmetric graph of the dimension I by j, or I square. I is the number of robots here. And the elements in the adjacency graph, adjacency matrix, is 1 if there's an edge between the pair of nodes, and 0 otherwise. And we can also express the degree of matrix, which represents the cardinality of the neighborhood. That means the number of neighbors, basically, for each node. And we can also define the degree matrix for both directed and undirected graph. And also, there's a very important tool that that we can use from the graph theory, which is called Laplacian, graph Laplacian, which is basically the difference between the degree matrix delta G minus the adjacency matrix A of G. So which will provide you a Laplacian matrix. Again, it's a symmetric matrix of dimension n square, n being the number of robots in the system. So which will provide us useful mathematical tools with which we can make the multi-robot control possible, and also we can analyze the theoretical properties of the multi-robot control algorithms. And so to come back to this Laplacian and also the general how the multi-robot control is connected to the graph theory later. And a graph, any graph can be connected when there is at least one path between each and every node. So if there exists at least one path for every vertex to every other vertex, then it's not connected. It can be completely connected when all the vertices are connected to all the other nodes. So that's completely connected graph. And there can also be a very sparse graph, like path graph or line graph, where one node is connected to the other node, and then the other node is connected to the other node, and so on. So either in a cycle or no cycle form. And there can also be tree graph, which is again a sparse graph, which there is no cycles at all in a tree graph, but they have some connection hierarchy. And also there can be dense graph, not necessarily fully connected, but still well-connected graphs. So these kind of properties will help us understand how effectively the multi-robot control algorithms can tolerate the failures in the network or noises in the sensor data. So as I said, we are dealing with rendezvous problem specifically, where the agents have to agree on a specific value of a parameter. The parameter could be the point of meeting when we say rendezvous in general. So let's say you have n dynamic agents, and they are interconnected via relative links, that is edges in the graph, and then the agent state or the robot state depends on the neighbors, basically. So the agent state being that their location or position and orientation of their position and orientation in a global context or global reference frame. And the objective of a general rendezvous problem is that the agents should meet at one point in space as soon as possible. And an example agreement protocol, let's say you have 3 robots in this case, 1, 2, and 3, and a simple agreement protocol could be that the velocity of the robot should be the average of the distance of the neighbors towards the location of the neighbors on average. So here, this link connections between 1, 2, 2, 3, and 3, 1 will pull them towards each other so that they finally will meet at one point, or as close as possible. So this is a very simple agreement protocol that has been used well as a baseline control mechanism. So when we can define the same agreement protocol mathematically using graph theory, we can use the graph Laplacian as I introduced before. So the velocity of each robot is minus the Laplacian times the current state of the robot, x of t. So the state of the robot again is the position of the robot in the global reference frame. And we can define this kind of state space representation of the of this simple agreement protocol for both directed and undirected graphs. So now let's get into the core research that I want to talk, which is the graph theoretic network graph aided, basically multi-robot control. So first I will be talking about how can we achieve consensus control, specifically using wireless network topology. So here, the objective is you have multiple robots in the environment, which having good communication capabilities, and they should be able to scan. Here we are assuming that they have direction of arrival sensor, which is basically directional antennas equipped on a robot, the directional antenna on a rotatory system, where we can rotate the directional antenna continuously and scan its environment to understand where the other robots are, especially the bearing, the angle. So the idea is that we build the connectivity graph using the sensed data from the directional antennas of the wireless communication device, and then we devise the control laws that exploits this connectivity graph and the direction of arrival DOA data, and to achieve the rendezvous where all robots coming together. So as I said, we are specifically using the direction of arrival of wireless signals because it has significant applications, potentials, both to use as a communication mechanism as well as the sensing mechanism. So here I'm going to talk about a new consensus controller based on consensus controller based on the direction of arrival of signal strength measurements, and we use specifically a simulation environment or even experimental environment called Robotarium. So Robotarium is a remotely accessible, freely accessible multi-robot testbed provided by Georgia Tech in the US. And we specifically use the Robotarium environment for simulation experiments that I'm going to introduce you soon. But this same Robotarium you can also use it to do real world, real hardware experiments as well. Currently it's free of charge. So if you look into this paper, the Robotarium, a remotely accessible swarm robotics research testbed, you should be able to get more information about that. And they also have a very good website, robotarium.georgiatech.edu. So what we do here is, when we propose a new control method, we will compare against state-of-the-art relevant controllers in terms of untest them or verify them against scalability and robustness. And especially we want to verify robustness to noisy sensor measurement, because the sensors are always noisy. So then how can we make sure that the control law that we employ in this multi-robot control mechanism can ensure that the rendezvous is achieved within some fine time. So as I said, we are going to assume the whole network topology of the multi-robot system as a graph, which is a connection of nodes and edges and the adjacency on the weight matrix. And we assume that the graph is initially connected. That means there's at least one way of information from one robot to another robot. And so this is the specific control law that we introduced. So you can see it's highlighted with W, the weight coming from the radio signal strength that we measure from the directional antennas, and we apply a threshold radio signal strength that can provide us a minimum threshold which it has to have to achieve some specific throughput. And that can be adjustable as well, depending on the context, depending on scenario, and can be dynamically adjusted as well, and also depending on the robot's capabilities. And also this control law involves also the phi of j, which is depending on the DOA of the measurements. So there are two measurements. One is the signal strength, which is the kind of magnitude of the signal, and then DOA is the angle of the neighbor. So we use both of them fused in this control law to make sure that we can guarantee the rendezvous objective. And while the robots are achieving rendezvous, they should keep their links. They can add more links, but they should not lose any links during this process. And this we can theoretically prove that this control law can help us achieve this, guarantee this link maintenance during the rendezvous process. And also they have to be distributed. That means a robot can only sense its neighbors and communicate with neighbors, and without any global coordinate frame of reference here. So they can sense the neighbor's position with respect to their own sense, not with respect to any other common frame of reference. So how can they? So these kind of assumptions and these properties makes them more applicable to real world. And our interest is in making sure that they are robust to control input measurement, that is sensor noise, and they are also able to work both in fixed or dynamic interaction topology. So interaction topology means the network graph. And fixed interaction topology means the robots have a fixed network graph about its neighbors, and dynamic means their assumption of or their understanding of the neighbor's location and the neighbor's position within the network graph evolves over time. So we verify the robustness, for instance, here to the sensor noise in the Roboterium experiments. We add some sensor noise to the sensor data, and see here you can see simulations of 15 robots and with a lot of sensor noise. And we can compare the proposed method, which is here, with the state-of-the-art and baseline methods. The baseline being the one that I introduced earlier, which is when I introduced the rendezvous problem, where they simply go towards their average location of the neighbors. And there are also several other bearing-based multi-robot consensus controller, again graph theoretic consensus controllers available in the literature, and we compared them against them. We also open source the codes. If you want to test these things yourself, you should be able to find the link and you see the paper. I will provide the links to the paper at the end of the slides. So here, for instance, some of the controllers cannot achieve the rendezvous in finite time, while some can achieve very slowly. And to make sure that they converge, they achieve the rendezvous, and also they maintain the link while they are doing the rendezvous, we also use Lyapunov-like candidate function to prove the stability and convergence from the theoretical perspective. So more details about the theoretical proofs you can find in the paper. I will provide the links to the paper or the references to the paper at the end of the slides. And after making sure that the method works in the simulations, we also implemented the method in the real hardware platform of the Roboterium. You can see these robots trying to rendezvous with and without sensor noises, and you can see that they are able to achieve rendezvous even under heavy noise conditions. So now I'm going to move on to the next part of the talk, which is to how do we achieve this multi-robot rendezvous when you have different set of sensors. Again, we have this mobile robot capability capacitated with the directional antenna, rotating directional antenna that enables us to measure the direction of arrival of the neighbors and also the distance of the neighbors. And in addition, we also have several other sensors suite on the robot to make sure it can avoid collisions with the other robots or collisions with the objects in the environment. And also it has proper onboard computing capabilities so that it can do the distributed computing on board. And we first built the global graph of the multi-robot system, global network graph, through the distributed communication mechanism. Here you can see the robot communicating with the other robots on their own neighbors, and then they will also share that information with the neighbors. So for instance, robot 1 is saying the robot 2 that, hey, my neighbor is robot 2 and 3. And then robot 2 will, again, on the other hand, will share his or her network information, local neighbor list. And by sharing, they continuously iterate this sharing process. And they will stop sharing when they do not have any more updates. No changes in the neighbor list of all the robots. And once they reach that condition, that means that they have converged to the global graph, ground truth global graph, so that they are able to share their information with the neighbors, and then continuously iterating it to achieve the building of the global connectivity graph in a distributed manner. And we also tested one. It's a simple but effective control mechanism where the robots track their neighbors in a hierarchical manner. So they first build the global graph. So on the right hand top right, you can see that this is the global graph that they built. And so they know, and then they create a tree in. So let's say they have to meet at the robot D, which is, let's say, predefined. They know that where they have to meet, but then how they are going to meet. So let's say here the point D or the robot D is the point where they have to meet. Then how can they achieve this rendezvous in a distributed manner? So what we did is we enable all the robots that are children to any parent. They have to just track their parent. They have to reach a rendezvous first with their parents, and this happens in a hierarchical manner. So the parents then collectively, along with their children, will go towards their higher level parents. And then this process repeated, they move higher and higher. And we made checks and balances so that they do not lose any robots on the way of this rendezvous process. And also we theoretically prove the convergence property that they will eventually achieve the rendezvous, and also they would not lose any robots on the way. That means they will keep the link maintained. They will maintain the link. You can see we conducted both simulation and real-world field experiments to verify and validate the proposed IDM. So here you can see that the robots are R1 and R1 first trying to go towards R0. R2 is trying to go towards R1, and then they both together go towards R0. And this is a simple 3-robot scenario. And this second scenario, you can see the robot, this is the initial network topology. That means the robot R2 is connected to R1, and then R1 is connected to R2 and R0, and R3 is connected to R2. And here we simulated a scenario where the robot R1 fails after, let's say, robot 2 reaches R1. In that case, since the robot R1 failed, robot R2 should proceed with the hierarchical tracking towards R0. So this is the end results. So R1, let's say we simulated a mobility failure where the robot is just rotating around its own place, while R2 and R3 met the R0. And the third scenario is where we kind of, again, it's a kind of fault tolerance scenario where we want to make sure it is tolerant, it avoids obstacles as well as it's tolerant to the failure in communication and mobility. And we also tested in terms of, to verify in terms of scalability, we tested in simulation environments because we do not have that many number of robots in terms of real hardware. So we limited the hardware experiments to just specific part of the properties, while we use simulation environment to test scalability, to increase the scale of the robots in the multi-robot system. So next, I want to talk about the multi-group herding, where we split the robots into multiple groups, and then they achieve both rendezvous and herding to a common destination for each and every group. And how can we achieve that in a distributed manner? And how can we use graph theoretic tools to achieve that? So I want to introduce this problem. So let's say you assume environment which is cluttered. So there are a lot of obstacles in the environment, and you assume a network graph of the robots. So each and every circle here is a robot, and then the dotted lines represent the link between the robots. So the connectivity graph. It could also be a sensing graph. And here you can see that the blue circles are the regular robots, while the green circles are the leader robots, which has advanced capabilities compared to the regular member robots. So here, the advanced capabilities we are assuming here is the perception, where the leader robots, only leader robots can pursue a specific destination that was given for them to go to. And let's say they have 2 destinations and 2 leader robots. So where each leader robot can take a certain group members to the specific destinations. And this kind of real world application has and it's a decentralized manner where the robots coordinate between themselves in a distributed or decentralized ways to achieve certain tasks. For instance, it could be autonomous recharging. For instance, leader robot could themselves be a recharge station for the member robots. They know where the recharge stations are. Now, it can be useful in coverage planning. So robots, specific set of group of robot, how to cover specific set of areas. So they have to split into multiple groups to cover certain areas. And they can also be applicable in information control problems. So again, some group of robot how to maintain information towards some certain direction, while some other groups should go into another directions or another locations. So first, we define rendezvous, multi-point rendezvous, that means multi-group rendezvous, as gathering robots at the leader in different groups. And herding is an extension of this rendezvous, where once they achieve the rendezvous, then they move together with the leader robots. So what we propose here is a distributed control strategy to achieve this multi-point herding. Again, it is an extension of the hierarchical tracking of the connected graph that we looked earlier. And we're specifically interested in the following properties, where we want to guarantee the convergence within each group. So there are multiple groups here. And we want to make sure within each group, they converge to the leader robot. And while they do so, they maintain the connectivity within the group. And also, we want to make sure that the leader robots are connected, so that we can also have the connectivity between the groups, not just within the groups. And also, we want to make sure that the control strategy is capable of handling minor faults, like the they are tolerant to robot failures, either mobility or communication failure. Again, as we assume that initially the robots are connected, not fully connected, but just connected. At least they are connected, and we represent the robot network as a graph with nodes and edges, and we assumed a single integrated model for the robot dynamics to simulate the robots. So I want to reiterate the objective, which is to assemble all the robots to their assigned leaders. And we assume that the leader robots are known. That means which robots are leader robots, we know that information already. So the approach has two prongs. So first is that we assign leader robots to each member robot in a distributed manner. So each robot chooses its own leader robot, depending on where it is and where the leader robot is, basically. So here we are trying to optimize an objective function, which is to minimize the shortest path distance along that network graph. And the second, once it chooses the leader robot, all the robot chooses the leader robot, then they use the distributed graph building algorithm to build the global connectivity graph. And then they realize this multi-point rendezvous, where within each group, they use the hierarchical tracking mechanism to go towards their leader robot. And we also made some checks and balances in the algorithm so that the leader robot can also start moving to the final destination, which is the herding process, either after the rendezvous is achieved or while the rendezvous is being achieved. Again, we convert the network graph into a rooted tree, because that makes the graph much sparser and makes much more easier to control. And we propose this algorithm where the leader robot or any parent robot waits until the children arrive within some safe connectivity maintenance radius. And once they achieve, they start moving, and the children also move while chasing the parents. And finally, eventually, we theoretically prove that, and also experimentally prove that they converge to the leader robot and they converge to the final destination that are set for the neighbor robots, for the leader robots. And also, we theoretically prove that the convergence works within the group and also between the groups to the final destination. And then the connectivity maintenance happens within the groups and also across the groups. And then the distance bound, that means they try to achieve this as fast as possible, or they travel as less distance as possible. We also use LabNow like candidate function to make sure verify the theoretical properties and analyze the theoretical properties. And we also use Robotarium as a multi-robot test bed for both simulation and practical experiments, because the Robotarium is freely available to test such a multi-robot application. So here you can see an example of the comparison of the multi-point rendezvous compared to some state-of-the-art controllers, multi-robot controllers like circumcenter-based control or coordinates-based controller. Here you can see 30 robots trying to achieve one specific one-point rendezvous. So that means they are trying to reach within 1 point. And you can see the robot 4 here is the root robot, where they have to meet. And you can see after the simulation that the proposed algorithm converged faster and with a smoother trajectory, while some of the state-of-the-art couldn't achieve the rendezvous. So we also analyze the convergence result by analyzing the LabNow function. And here you can see multi-point rendezvous, where you have multiple robots assembling into multiple groups, either 2-point or two group here. For instance, you have 13 and 15 as the leaders, and then you can see here 3 into 3 groups. So they all distributedly communicate between themselves and figure out who their leader robots are. Once they figure out the leader robots, they build the graph. Once they build the graph, then they communicate within the group to achieve the rendezvous at the group leader using the hierarchical tracking of network topology. So here you have 3 groups and 3 leaders, and here you have 4 groups and 4 leaders. And here you're going to see how they are, how we can achieve the rendezvous while how we can achieve the herding after the rendezvous. So in this example, the herding starts after the 2-group rendezvous is completed. So all the robots go towards their leaders 13 and 1, while the final destination is the points indicated with stars. So once they achieve rendezvous, they are now moving towards their final destinations. So this is herding after rendezvous, and we verify that this is possible. And then we also verified this multi-point rendezvous and herding together. So that means they do not wait until the rendezvous is achieved. The leader robot starts moving before the rendezvous is achieved, so that they can save time and they can be more efficient, while also making sure they can always converge. So here you can see that they achieved faster herding compared to the previous example. So this is also another example where both herding and rendezvous started at the same time. So this is much more faster than the previous 2 examples, while still keeping the convergence properties. And this is an example of the same multi-point rendezvous. So this is for instance, this is single group rendezvous experimented in the Robotic platform, the hardware platform. So initially so these are initial locations, and now the algorithm is started, and now they are trying to achieve in a meter the single location. And now this is 2-group rendezvous. So it takes time for them to go to their initial positions first because of the Robotic platform, and then they are trying to achieve to rendezvous in 2 different groups. And now this is about an example of multi-group herding. So once they achieve rendezvous, then how can they? So this is the initial locations, and now they're doing herding and rendezvous at the same time. So once they achieve rendezvous, then they move towards their destination here and here. So I want to thank you again to listening to my talk. So I want to summarize what I have presented, what we talked so far, that the multi-robot control has tremendous potential to real-world applications, and I also introduced you to the challenges associated with the deploying multi-robot systems in our real-world applications, and how can we deal with some of the challenges. And then I also introduced you to graph theory and graph theoretic tools. How can we use them in enabling multi-robot control applications? And we looked at specific examples of how do we use graph theoretic tool or graph theoretic control laws to achieve the multi-robot rendezvous, multi-robot consensus control, and multi-robot herding. And I also shown some examples of how do we prove these solutions experimentally, especially when using the Robotic platform that I presented, in terms of scalability, efficiency, the tolerance to failures, and also the dynamic properties of the control law. So here I provide 3 references, the 3 papers which I used in this talk today. The first one is the consensus control of distributed robots using direction of arrival of wireless signals. which was presented in the Distributed Autonomous Robotic Systems Conference in 2018. And then the second paper is about multi-robot rendezvous based on bearing-aided hierarchical tracking of network topology, which was published in an ad hoc networks journal in 2019. And then the third one is the multi-point rendezvous in multi-robot systems, which was published in the IEEE Transactions on Cybernetics in 2020. And you can also always check out more research that I do in my lab at hero.uc.edu. And thank you very much for your attention, and thank you for staying with me in the evening time. Thank you. So if you have any questions, please let me know while I just present some of the other research that we do in our lab.
Thank you, sir. So now I request to participants, they can ask their queries, whatever they have. Yes, from the participants. You can write your queries in chat box also.
There's one question. Is it possible, if possible, kindly send me the link? I don't know what link. Is it for the presentation link or?
Participants, please firstly ask your queries. Then the link will be shared after that. No issue of link. So if anyone have any queries regarding robotic session, then you can ask with our professor. Yes, anyone? Yeah, sir, we are just seeing the chat from the chat box. Your lecture was very much informative and it was very great session. I think participants are just informing that only in chat box.
Okay, yeah, thank you. Thank you for listening to the talk. No.
Thanks a lot, sir. You have shared your valuable time with us. We are very much grateful to you, and in future also, we just expect that you will be with us in such type of events. So from this, just I end up this session.
Okay.
Thank you, sir. Thanks a lot. We are very much grateful to you, sir. Again, and thanks to all, sir.
Thank you. Thank you for providing this opportunity to talk to you guys. Thank you.
Thank you, sir. Thank you.
Have a stay safe and have a nice week.
Yeah. You too, sir. Be safe and take care. Thank you, sir.
Thank you.
Sir, are you there?
Yes, I'm still here. I'm trying to figure out.
Just a minute. One of the query I have seen on our YouTube link. That is just a minute, sir. I am sharing in chat box also. So I think A-bar has raised a query. Sir, how does a swarm robotic model work?
Can you repeat the question? How does the swarm robotic?
Just a minute. Model work. I have also pasted in chat box. So,
okay.
Yeah.
So I think as I understand the question, how does the swarm robotic model work? So I think the question is about how can we make the swarm robot control possible. If that's correct, so again, the same thing that we talked in the in this presentation is applicable also for the swarm robotics, where in general in swarm robotics the control is more centralized traditionally. That means there's a centralized controller which understands the state of the individual robots of the swarm, and accordingly they provide the control inputs to the swarm in a more centralized fashion, because swarm robots are generally much miniature than the real world multi-robot system. And swarm robots also have very, very low computation capability. So they cannot enable, or they cannot achieve much distributed tasks. But there are recent works that exploits graph theoretic tools also enabling the swarm robot control in a distributed manner. I hope this answers the question.
Thank you, sir.
Okay, no problem.
Thank you, Ram. Thank you for with us. Your session was very good on multi-robot control mechanics, and we hope that in future also you will be with us to deliver your knowledge or wisdom or words of wisdom with us. So thank you so much.
Thank you, Anupan. Thank you, Vipin. Thank you
Thanks,
for.
sir. Thanks a lot, sir. Thanks.
Bye.
Okay, sir.
So I just close the tab, right?
Yeah, you can leave, sir. Okay,
Yes, sir.
Okay.
Thank you, Ram.
Bye.
So for the participants, we have just completed day 4th of our faculty development program. So, and I am also seeing the queries regarding next day. So we will just send you on mail after this session. And also, I think all the feedback link has been shared for today. So with this, I am just end up this session. So thank you. Thanks a lot, all of you with us. So on the next day, we will start the session from 10 a.m. sharply. So be with us at sharply 10 o'clock. Thank you. Thanks a lot for your patience and for your cooperations. Yeah. Okay. Thank you. Thanks a lot.
You again. Yes.